So we're going to do some memory refreshing on this chapter. Like, what does molarity mean? So let's just rewrite out the equation. Big M means molarity. Which is also called concentration. They mean the same thing in this chapter. And big M equals moles divided by volume in liters. Molarity equals moles per liter. And if you know any of the two out of the three, 1, 2, 3, you could solve for the third. You can rearrange this a bunch of different ways to solve for the third. Okay? So this is a very important equation in this chapter. So this says, how would you prepare? So now we're going to start actually making the solutions themselves. So let me, oh, I can't write on this? Oh no. How would you prepare a 1 liter solution of 0.15 molar sodium chloride solution? So let's look back at our equation. I gave you 1 liter. Oops. And I also gave you 0.15 molar, big M. So in other words, I gave you big M and I gave you liters, right? So when I ask you how you would prepare it, if you're making salt solution, you're using salt and water, where salt is a solid and water is what's going to dissolve the salt to make it a solution, okay? So if I know molarity and I know liters, I can find moles, right? If I know the 2 out of the 3, I could find this guy. So let's just do that for right now. Let's plug these numbers in where they belong. 0.15 molar goes here. So 0.15 molar is the number I gave you. And how many liters did I give you? 1 liter. So if I rearrange to solve for moles, what do? Well, I multiply both sides by liters, and luckily it's just 1 liter because that's the number that was given in the problem. Now I'm going to rewrite my big M so you can see how the units work out, okay? Because big M stands for moles per liter, right? So that's what allows the liters to cancel out and leave us with moles. So 0.15 times 1 is 0.15, okay? So 0.15 moles. Now, who is this of? Well, I asked you, oops. I'm asking you to make sodium chloride solution. Who is sodium chloride? First of all, what's its chemical formula? Sodium chloride, right? This is salt. So basically, they're asking you to make salt water. So the thing becomes, give me 1 second. All right, so hopefully you can see me. Okay. This is salt, right? This is just like normal table salt, sodium chloride. That's what's in this thing right now. So this is what I have to make my salt solution. So what am I going to use? I'm going to use salt and water, right? That's how I'm going to make the solution. Why? Water is like readily available, right? So I have salt, and now I know how much salt I need, right? I need 0.15 moles. So I give you this, and I hand you this, and I say, hey, go measure out 0.15 moles. Do you think that there is any tool in my classroom, and I know it's hard because we haven't been in here, right? But any tool in my classroom that measures in moles?
We don't know.
So the answer is no. There's no tool in my laboratory that measures in moles. What can I turn moles into mathematically? Grams, right? Do you think I have a tool in here that may measure in grams?
Yes.
I absolutely do. It's an electronic balance. So after you find moles, if I'm asking you to prepare the solution, you need to turn it into grams because there's no tool in my laboratory that measures in moles. So we're going to turn my 0.15 moles into grams using dimensional analysis. So let's do that. So this is 0.15 moles of sodium chloride. How do you turn moles into grams? You use the molar mass from the periodic table. For every 1 mole of sodium chloride, it's 58.44 grams. A sodium plus a chlorine, this is what it adds up to. So let's calculate that out. So what does that equal? Okay, now technically sig figs, oh no. Oh yeah, okay. Is 2. This was 1.0 liters, 1.0 liters. So it's 8.8 grams. Okay?
Right. So it's 8.8.
No, 8.8 grams.
Okay, so should I just put that in, or do I put in 8.76?
No, it's 8.8 grams. All right.
Do I also have to write
You have to write 8.8 grams.
Yeah, no, I meant like the equation, like the example.
Do you have to write the what?
The example thing for like the equation that just happened.
I would write all of the things that I'm doing right now. All right. So, what does that mean? Well, the whole thing is now is, right, we've been doing all of this math and crunching all these numbers, and you can get all these numbers, but you have no idea what it even means. I just asked you to make a solution. I want it to have a specific concentration, and I want a certain amount of it. So here's the common way in chemistry we make solutions. Hopefully you can see me. I have this flask right here, okay? It's called a volumetric flask. It's glass, and if you notice, it says 1,000 milliliters, which is 1 liter. Why did I pick this size out? There's a reason I picked this one. I went in the back and I have tons of these different sizes. Why did I pick this one? Because I asked you to make 1 liter of solution. So I picked a tool that measures out 1 liter. Here's the cool thing about this flask. It only has 1 mark on it. It's really hard to see. 1 mark. So this flask measures out 1 liter beautifully. Here is the bad part. You can't measure out any other volume in here but 1 liter. So sometimes we don't use volumetric flasks. Sometimes we use graduated cylinders to measure or to make a solution because they have more markings on them, okay? But I do have a 1 liter flask, so I'm going to make 1 liter. So what do? Step 1, and yes, you need to know these steps. And I'm actually going to do them. I'm going to make the solution. So step 1, for preparing a solution. Measure out 8.8 grams of sodium chloride on an electric balance. Yep. All right, so I'm going to plug my electronic balance in. We'll see how well I can do this. So I have this thing right here. It's called a weigh boat because you never dump chemicals straight onto a balance. You either dump them in a container. This is called a weigh boat. You can dump them into a beaker. It doesn't matter, but you're never going to dump chemicals straight onto a balance. So I'm going to show you my balance over here. Okay, I need to turn it on. Hopefully it'll turn on. Wow. Okay, so it's turning on. And then I'm going to put the weigh boat on it right now. And I'm going to zero it so that it pretends it's not there, right? And now we said we want 8.8 grams. So I'm going to dump this on here until this reads 8.8. Now my balance measures out to the thousandths place. So if I have a couple of digits after the 8, it's going to be okay. So I'm going to go slowly. Can you see the numbers changing at all? No? Let me see if I can move it closer. Can you see it a little bit better? Sort of? Okay. So I need to get it to 8.8, right? Oh, whoa. See how quickly that changed? Okay, now I know this is salt and I can touch it with my fingers, but technically in this class you would never want to touch anything with your fingers. So we have what are called a scupula, which we used in the other demo, right? Or other lab I did. And so I'm a little bit over, so I'm going to take a little bit out. Take a little bit more because it's like 8.85 and that's better. Okay, so look, I've got my 8.8 grams of my solid. Okay, now what am I going to do? Well, I'm trying to make 1 liter of the solution, right? So I got my flask. Here it is. Now I want to dump this in there, but the thing is there's a good chance it's going to spill. So I usually use a funnel to help get the solid in there. Okay, so I take my solid, dump it in here. Boom. Okay, now I have the solid in the bottom. So I'm going to say next step. Add the sodium chloride to a volumetric, that's what it's called, flask. This could also be a graduated cylinder. I am choosing the tool of volumetric flask right now. Ooh, graduated cylinder. Okay, so that's what I've done. I've measured it out. I'm literally doing this for you step by step, right? Now here's the really important part. You do not want to fill up to the line instantly. This is very, very important. You do not just bam, dump all the water in here until you're here. You don't do that. This is a special technique. You need to get all of the solid to dissolve before you fill up to the line. So what am I going to use as my dissolving agent? Water. I'm making a solution with water. So now I got to find my water. Now we usually would use what's called distilled water because it is pure. It doesn't have any impurities. Like our tap water has minerals and stuff in it. And so if we're trying to make a pure solution, you don't want like minerals and stuff in it. So in these bottles in my classroom, it says DH2O. It means distilled water. And it says pure water. Now, I'm not going to be able to. I probably should use a funnel for that too. Okay, and the cool thing about these flasks for making solutions is that you have the ability to swirl without stuff flying out of them. So look, you can swirl and swirl and swirl and swirl. So what did I just do? Next step, add enough water. So 3. This is a 4-step process.
You mind if slow down so I can like break down the rest of this.
So add enough distilled water to dissolve all of the solid. And in this case, my solid is sodium chloride. So I'm going to swirl some more. Right? We know salt readily dissolves in water, right? So this is kind of like a question that they asked on the lab yesterday. Now, in chemistry, we tend to not taste our chemicals, but this looks like water. So how do you know if something's dissolved in it? Well, there's a couple of ways. Technically, since it's salt water, you could taste it and it would taste salty. That would be a way to know that it's not pure water, right? What else could we do? If we heated this up, we could get the salt back. We could evaporate all of the water and the salt would be left in the bottom of the container. So we could figure out if there was something dissolved in here those two ways. But as of right now, it doesn't even look any different than pure water does. It looks the same, yet it's not. It's salt water. Okay, so just because I have something that's colorless up in the front of the class doesn't make it water. I showed you acid before. It looks just like water too. So you can't just assume that something is colorless, that it's water or clear. We don't use the word clear in here. We use the word colorless, okay? So now that all of the salt is dissolved, so I'm going to walk this around the room just real quick. You can see that there's no salt in here. All gone, right? Okay. Now we're going to pretend we're going to use distilled water, but I'm going to cheat because I don't have enough distilled water. Now that it's all dissolved, then you can fill to the line. So fill up to 1 liter with distilled water. So that's the last step. So 4 steps. Measure it out. Put it in a flask or a cylinder. Add enough water to dissolve. And once it's all dissolved, fill up to 1 liter, because that's how much they asked me to make, with distilled, that's what the D stands for, water. So I'm going to go over to my sink and we're going to pretend that's distilled water. Okay, and then you would normally, so I have it right here, it's filled right to the line, right? You would normally stopper it, right, and shake it so that it's all mixed, right? You would never use your hand like I just did. Okay, and now what do I have? I have 1 liter of a 0.15 molar sodium chloride solution. I just made a solution from a solid. Any questions?
Can you show me 4? Yeah, sorry.
Sure. So here are the steps. It's a 4-step process. I guess technically you could call it 5-step because you first need to do the math. The math needs to be done first, and then you use the math in descriptive ways. So we're going to do another practice one.
I still don't know what the equation was for the last
What equation was for what part?
The math part of putting
It
force
was the
across.
equation that we've used most of this chapter, this one. I gave you this number, and I gave you this number, so we solve for this one. All right. So, when you're asked how to prepare a solution, it's going to be math with a step-by-step explanation. Okay? So, when you see this, oh, like I said, I can't draw on it, shoot. How would you prepare? You know you will not only have to do math, you will also have to do the steps. And we're going to do another practice one. All right. This right here is just explaining what we just did. It's just written in a sentence. Okay. Let's try another one. How would you prepare 5 liters of a 1.5 molar solution of glucose? So let's see. 5 liters. Let's do some basic things. I gave you the concentration, molarity. I gave you the liters, the volume. We can rearrange that to find moles of glucose, right? So the molarity is 1.5 molar equals moles, that's like my X, right? What I don't know, over, and they want 5 liters. Molarity equals moles per liter. So now I can rearrange and solve for moles. So 1.5, and I'm going to rewrite big M as moles per liter just so you can see how the units work out. Right, you multiply both sides by 5 liters. So you get 7.5 moles. Now, 7.5 moles of who? Well, the substance in this case is glucose. So this is like your solid. Now, because I don't have a tool in my laboratory to measure out in moles, I need to convert my moles to grams so that I know exactly how much to put on my electronic balance. So 7.5 moles of glucose. And then 1 mole, this is periodic table, 6 carbons, 12 hydrogens, 6 oxygens. I'm going to wait until you guys find its molar mass. You guys have depended on me for molar masses. I want you to find that guy's molar mass. So here's the molar mass, right? I know with sig figs this is the number, but I'm going to be honest with you. In a real life lab setting, you would use the exact number. Okay? In a real life lab setting, you would use the exact number because if you add 49 extra grams, you're not going to have the right concentration. But in terms of sig figs, it's 1400. Okay? So now that I know how much of my glucose I need to measure out, I'm going to start my 4-step process. 4 steps. So here we go. Oops. Measure out 1,400 grams of glucose, it is important that you name the tool. On an electric balance. Step 1. Add to a, either volumetric flask or graduated cylinder. 3, add enough water to dissolve all of the solid. And then finally, finish. Fill up to, how much did I ask you to make in this problem? 5 liters, right? So that's where you fill up to. 5 liters with distilled water. So I'll give you a second to keep writing this down. So the math isn't really new so far. What's new is how to actually describe how we're applying the math. So if you do this, what has happened? You have created a sugar solution, glucose. You have 5 liters of it, and its concentration is 1.5 molar if you do these steps right.
I wasn't done writing down the steps.
So now we need to discuss dilutions. Dilutions happen whenever you mix any two solutions together or whenever you add water to something, okay? And this is the equation for dilutions. M1V1 equals M2V2. You don't need to memorize it. I'll give it to you. Where M1 stands for concentration or molarity. V1 stands for volume. M2 stands for a new molarity. And V2 stands for a new volume. So starting ones, ending ones. Now, unlike our molarity equation, our original equation that we've been using, this one, this is the one we've been using so far in this chapter. Unlike this equation, where you have to use liters.
The dilutions?
Yep, I'll be back in a second. So this equation right here that we've been using so far has to have liters. There's no exceptions. Always liters. The dilution equation can use liters or milliliters. And the reason that is because volume is present on both sides of the equal sign. And it's not on the molarity equation. So you will have the option of plugging in milliliters or liters into here. Now just be careful, you do not have that option in this equation. This can never be milliliters, ever, 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 ever. It will always be liters because liters is only on this side. It's not also on this side. Now the math for this is actually pretty easy as long as you can read the problem. So if I have 125 milliliters, so there's my volume, V1. And a 0.15 molar sodium hydroxide solution, so that's M1. And I add 25 milliliters of water to it, okay? If you add water to something, it dilutes it, right? We were talking about this before. If you're making Kool-Aid and it's too sweet, what do you do to lower its sweetness, aka concentration? You add water to it. It's a dilution. That's what makes it taste less sweet. That's what by less sweet, it means less concentrated, okay? So what happens to the molarity of the diluted solution? What will the molarity of the diluted solution be? So what are you solving for? You are solving for M2, the new molarity. That's what it's asking. You don't know? Now, you have to be very careful for V2. What is the new volume? And this is where kids get mixed up. Is it 25? If you have a 25 milliliters of 125 milliliters of stuff and you add 25 milliliters of water to it, your new volume is 150 milliliters because there was this much and then I added this much more. So now at this point, this is not hard math. You plug and chug. So M1 V1 equals M2 V2. So M1 is 0.15 molar. V1 is 125 milliliters. M2, I don't know, you can call it X if you want. And V2 is 150 milliliters. This is very basic algebra. What do? I divide both sides by 150 milliliters. So the new molarity will be 0.15 times 125 divided by 150. 0.125. Is this a 2 sig? Oops, sorry. Let's see, 2 sig fig number. Yeah, the 0.15 and the 25. So you can call it 0.12 or 0.13 molar. Doesn't matter. So what was the concentration to begin with? 0.15. The concentration went down to 0.13. Why? Because you diluted it with water, so it's less concentrated. You have a lower concentration than before because you added water to this thing. Okay, so the question becomes, how is this different than the last problem? And I'm going to tell you the easiest way to recognize this. So I'll leave this up for another second. So the other problem, we used this for molarity, right? And we were given, for example, 2 out of the 3. Dilution, so there were 2 numbers given. For dilution, besides the wording where you see the word like dilute, they gave us 3 numbers. You can't use this equation up here when you have 3 numbers. Well, I shouldn't lie. You can, but it usually involves stoichiometry if you're up here. So when you see 3 numbers, and this isn't always true, or the words diluted or added water or whatever, it's going to be this equation because you have too much stuff to technically plug in here for right now. Okay, so try another practice one. And this one's going to have a little bit different wording. So this problem says you have 100 milliliters of a 0.15 molar sodium hydroxide solution. So let's do our M1, V1. M1, V1. Okay. And then it says, what will be the molarity? So M2 is your unknown. I don't know. That's your X. If I dilute it to, now notice this diluted to as opposed to added to or mixed with is not the same. Dilute it to means 150 is your final volume. You do not add these two together. In order for you to add the 100 and the 150, it would have had to say mixed with, added to. What they've done is they've taken 100 of this and they've added 50 more milliliters to get it up to 150. 150 is your final volume. So the wording is really important. So V2 is 150 because it says the words diluted to. That means final volume. In order for you to add them, it needs to say added to or mixed with or combined with or something like that. So M2 is my unknown or my X, if you want to plug it in as X. So here's my handy dandy equation. 0.15 molar. 100 milliliters. M2 is my unknown and V2 is 150. It's very easy math. So how do I get this by itself? I divide both sides by 150. Look at my milliliters cancel out and I'm left with molarity. So this ends up being 0.1 molar. 1 sig fig. NaOH, I should write that up here. Sodium hydroxide. Okay. Be careful on this one. I want you to try this one by yourself. All right. So in this problem, you have 345 milliliters of a 1.5 molar sodium chloride solution. But then they heat it to try to get rid of some of the water. So they get rid of 120 milliliters of water. So first things first, this is my first volume, V1, and this is my first molarity, M1. What's a good hint that I'm going to do M1, V1, M2, V2 is I'm given 3 numbers. That's a hint. Now, this doesn't always work, but it works for just right now. M1 is 1.5 molar. V1 is 345 milliliters. It says they want the new molarity, so again, we're solving for M2. And 120 milliliters of the water evaporates. So what is my V2? Is it 120? Is it 345 plus 120? We're going to lose this much, right? So we won't have 345 milliliters left at the end. If you get rid of that much water, You only have 225 milliliters of stuff at the end. So now this is the dilution equation, but this is not dilution. This will be more concentrated now because you lost some of the water. So M1 is 1.5 molar, V1 is 345 milliliters, M2 is my unknown, and V2 is 225 milliliters. So this comes out to be 0.23 molar. Uh-oh, did I do something wrong? Ooh, sorry. My 5 stuck on my calculator. 2.3 molar, sorry. So my original concentration was 1.5, but when I got rid of some of the water, it became more concentrated. So let's say you put too much water, technically. Let's say you make your Kool-Aid and you dump all the Kool-Aid in there. You're right, and you're like, oh, it's not as sweet as I want it. So you have two options. You can dump more sugar in there, right? Or you technically could heat it and get rid of some of the water and it would taste sweeter because some of the water would evaporate and therefore it'd be more concentrated. Obviously, the easier route would be just to dump more Kool-Aid in there, right?
Just evaporate the Kool-Aid, it becomes a hot, sweet drink.
So yeah, if you evaporate it, it'll be hot, but when it cools down, it'll still be cold. It'll go back to room temperature, and because the Kool-Aid or the salt in this case is a solid, it doesn't escape out of the container. It'll stay in there. Just the water would evaporate.